Hi, everybody. First of all, I hope you had a great spring break, and thanks in advance for your patience as I work out some kinks. This is the first time I'm trying a video lecture, so see how it goes. Anyways, lots to talk about today. Lots of scary things with the coronavirus, COVID-19. I hope you guys are all staying safe, staying healthy. Please let me know if I can do anything on my end to help. In the meantime, we'll be sort of, I guess, having this remote format. And so let's go ahead and get started. I'll go ahead and show the lecture plan for today, and then I'm going to go back to the computer. You can see, sorry again, we're still kind of figuring out some kinks about how best to present this, but here's our normal sort of intro admin, last time, and goals for today. I guess I was a little bit too eager to write this lecture plan. You guys are still out and about, not yet back at USNA, but again, I hope that you've had a great spring break. Again, stay safe, stay healthy. We're transitioning to an online format. That being said, I'm going to assign officially homework 7 and in class 7. I'll post both of those on Blackboard today. And both of them are due next Friday. I'd like to try to keep with the schedule of exam 2 being Wednesday, April 1st. So we've missed 2 class periods, but I think we'll be able to talk about this new unit of API design intro, and then we'll stop with that. That being said, more on this to come, but plan on having lots of time sort of during those scheduled office hours, those online office hours, to be able to work on homework 7 and in class 7. I also wanted to take a moment to kind of talk about where we are in the course. I think with this transition and with spring break being last week, this is sort of a good opportunity to revisit our student learning goals. So I would say we could put a big check mark next to our analyze indeterminate and determinate structural systems with the direct stiffness method. That was sort of the main point of, a lot of exam 1, the first 5 homeworks. And then we, the last couple weeks, have been working with STAD to analyze these structures using computational finite element software. I think you guys did a great job on your homework. I have a big stack in my office. Some feedback overall, but depending on how things go, we'll maybe sort of table any actual stat analysis and keep things to more of a general questions of process and filling in dialog boxes for that. Next, we're going to move to API design guidelines. So we're going to be talking about, once you have your deflections and you know your loads, how do we know if those loads are safe? So how much is too much in terms of loading on a structure? So sort of that's where we are so far. This is the last topic that we'll cover before exam 2, and expect some review material from me. I'll post that next Wednesday. I also am going to jump over, so today, sort of goals for today. I'd like to give you guys some feedback. Thanks for filling out quickly the SOS questionnaire I sent you guys about what works best for online. This is kind of an experiment, so again, please feel free to give me some feedback about what's working, what's not working, and hopefully we can make adjustments on the fly. I'd like to then briefly introduce this new unit of API design guidance, and we'll start on a column design example. There's 5 main checks. I like to liken this to sort of a bracketology. No NCAA tournament this year, sort of a little bit too real, but at any rate, we're just going to do the first check today. The first check is the longest, and then we'll hopefully be able to finish all of the last 4 checks next time. So let me share my screen, and let's share my screen. And pull up just a little bit of the feedback you guys gave me about the online classroom. I'll do this in presentation mode. Great, so thanks again. We had 35 people respond as of midday on today's Sunday, the 15th of March. I know this is sort of a quick turnaround, but I wanted to try to get some of these nuts and bolts down pat, so doing it quickly. Looks like we've got the majority of folks on the East Coast for the next week or so, with Central Mountain and Pacific all represented. So I'm trying to keep that in mind. hopefully this format works with me pre-recording a video and then you guys can watch it whenever is convenient for you. In terms of lesson format, again, hopefully we'll be able to sort of do a similar document style notes. I'll write the notes with this camera, and hopefully you guys will be able to pause it and sort of do things on your own notes, and then I can do the solution and we can go from there. People made really good comments that if we were to try to do live stream crashes, we might have difficulties with everyone signing on at the same time, or the live stream could crash. So I thought those were really good points, and it seems like the majority of folks think that pre-recorded lessons will work best with their schedules. So that being said, I would like to have office hours during Monday, Wednesday, Friday, so sort of like a traditional class period. If things are going great, awesome. Feel free to at least please sign in once a week just to touch base with me, let me know things are going well. I also think these online office hours, we can think of it sort of like flipping the classroom. If you plan to work on the homework during these office hours or to work on the in-class problem, you can kind of ask me questions in real time. So we'll talk about that next. Looks like most people think that they can open an MP4. I think that should work. If you find that you're having an issue, please let me know and we can make some, adjustments with that, or try to, I guess, troubleshoot any issues with the technology. And in terms of office hours, it looks like it's a fairly even split of the times I selected. So I tried to sort of split all of the times that people said, and how about 9:30 to 10:30 and 13:30 to 14:30 Eastern time? If neither of those times would ever work for you, please send me a note and we can definitely arrange EI by appointment as needed. My plan is that I will be online. I'll send out a Google Hangouts link, and I'll be online during both of those hours every Monday, Wednesday, and Friday. And you can sign on for as many or as few of those office hours, with the exception, I'd like you to at least check in with me once a week. That's sort of a, just to make sure that things are going well, you're able to access the videos, and if you have any questions. Again, I think this would be a really great time to work on homework, work on in-class problems. I can definitely answer any questions that way. And we can also have some discussion with other folks who sign on at the same time. In terms of turning in assignments and me sharing assignments, it seems like there's a fairly even split. I am happy to send you guys, I don't want to inundate your email inboxes, so why don't we plan for now on me posting things to Blackboard. I know that sometimes Blackboard has outages or there's sort of issues accessing Blackboard, so if that happens, let me know and I can send things via email attachments or share things on Google Drive. So let's be flexible with that, but try Blackboard as plan A. In terms of submitting homework, this was even more kind of a 60-40 split. It looks like Blackboard is probably going to be the plan of choice. I think that might be the easiest for at least keeping things organized. But that being said, if you're having an issue with uploading into Blackboard, just send me an email and I can print it out or just put a check mark, kind of look at the digital copy myself. So pretty flexible with turning it in. Just let me know if you have questions. A few people asked in the comment section if they can just send in a photo of the assignments, like take a picture with your phone. Absolutely fine. So please, don't feel like you need to find a scanner or a printer. As long as I can read the work, then that's totally fine. Other things, nuts and bolts. Again, I think Google Hangouts is going to be the platform of choice for our online office hours. And I will send an email in the link and also make an announcement on Blackboard. So hopefully we'll be able to address any issues, this Friday when we have our first, test run. And Wi-Fi issues, I'm cautiously optimistic. Also, I think that there shouldn't be too many Wi-Fi issues, but I'm sure that we should expect the unexpected. So we'll just have to see what happens. Thanks in advance. A lot of you guys were really positive and have a great attitude towards this transition to online learning. Hopefully I'll be able to see you face to face sooner than later, but definitely I think, these are weird, crazy times we're living in. So I appreciate you guys being so flexible. Also, some of you mentioned that you have friends and siblings in the same situation at other universities. So please let me know if they have any awesome tips for teaching online or this online classroom. I would be more than happy to try to incorporate that into our plan. A few folks also had questions about STAD. I'm trying to get VPN access for everybody in EN 441, which means basically if you connect with this VPN, you can make your computer think it's on the yard, and so you could access STAD with no issues. For now, I'm thinking that we have enough things going on with this transition that we will plan on keeping STAD to a general process-based questions, or filling in the dialog boxes like in class 6, and no more actually having to run the program. I'll let you know if we get any progress with the VPN access. A few other people mentioned that there were some password issues. People's passwords are expiring and you have to change it on the yard. Send me a note if that's an issue. I've reached out to our department chair to see, sort of what's being done about that. I'm sure there's a lot of people in that situation, so hopefully we can, figure that out sooner than later. But just let me know, keep me posted, and let me know what else I can do to help. This is normally where I say, are there any questions or comments? But I realize that no one's here at this moment. So let's just keep plugging along. Please, though, if you do have questions or comments, feel free to shoot me an email, let me know in office hours, and we'll go from there. So that is it for online classroom. I'm going to close out of this. Oh, one thing I did want to show you, I'm on Blackboard now. So this is sort of the view I think you guys have. My plan for the online materials, if you go to course materials, I made a new folder called online lesson material. And my plan is to upload a folder for each online lesson with the lesson number and the date. And in that folder, I'll have any handouts or PowerPoints that we are going to talk about. So this online classroom survey results was basically the PowerPoint we just went through. We've got one more PowerPoint and one handout today. And then I'll also upload the video lecture. This is just a test right now. I'll take it down and replace it with this one. The last thing I'll do is I'll scan in and upload the notes that we take during today's lecture, and we can hopefully keep things in this folder. Let me know if this organization seems like it'll work for you, or if there's a better way that you think to sort of keep everything in one place. That being said, let's go ahead and shift gears and start talking about the American Petroleum Institute design guidelines. So we've talked a lot about offshore structural analysis. Now we're moving into offshore structural design. So this is just a really brief introduction PowerPoint to kind of give you guys a flavor of what types of offshore structures we have and what's out there. I like to emphasize that our course name, or course title, is Ocean Engineering Structures. So pull up my laser pointer. So again, emphasis on ocean here. We're going to be following a lot of offshore platforms, offshore oil rigs, and things like that. So what types of things might we find when we're talking about offshore construction? The first question you have to ask yourself, there's two main flavors of offshore construction. There's fixed, which means you have a pile that's driven all the way into the seafloor, and the platform is fixed to the seafloor. So that's sort of what this artist rendition of this platform is over here. You see them driving some piles into the ocean over here. There's also floating platforms, which are often in very deep water, and they're sort of counterweighted. Very cool, but outside the scope of this course. In terms of these fixed platforms, though, they're commonly used for a lot of different industries. Some examples we have are oil platforms, which are a really common driver for offshore construction. Lots of offshore drilling in the Gulf of Mexico, other places. So here are just some cool offshore oil platforms that I found from stock photos online. One really cool one is this Berkut oil platform. It's the largest oil platform in the world. It's located off of the Russian Pacific coast. Really big, really heavy, and something that I thought is cool is it has to put up with a really extreme environment. Not only is salt water very corrosive, as you guys know from your materials engineering class last semester, but we also have to deal with freeze thaw conditions, subarctic, very, very cold temperatures. I guess there's some seismic earthquake activity there, and they can get really big waves. So 52 feet, I think that's a lot. Anyway, so these things are really, you can design enormous structures in the offshore. Also, there's a growing application of offshore structures for wind energy. A lot of the structures we're going to be looking at are going to be sort of this monopile, so a single pile, and then we're going to be analyzing that column for its safety. A lot of offshore wind farms are in Europe, but we're definitely enhancing offshore wind here in the US. So sort of pretty cool stuff. But when we're thinking about these different designs and these different structures, it's really important that we can estimate, first of all, what are the loads? So can we predict what these wave loads and what these wind loads and rain loads, et cetera, are? And also, can we determine how strong our structure needs to be built in order to successfully withstand those loads? Because we really have to be able to avoid structural failure, which can cause operational failures. It can cause loss of life and very serious consequences when these structures fail. And the way that we think about how to design these structures is by coming up with the design guidance. So the design guidance that we'll focus on in this class is the American Petroleum Institute's, or API's, recommended practice, planning, designing, and constructing fixed offshore platforms working stress design. This is a really big trade organization focusing on oil and natural gas, and that's why we're using it, because they have a lot of offshore applications because there's so much offshore oil drilling. It has very widely accepted standards. We have the 2002 manual. Not much has changed, but it has been updated most recently in 2014. I posted the full manual to Blackboard. It's 242 pages long. Don't worry, the crux of what we'll be going through can be summarized in about 4 pages. So I have a handout that I'll show you guys in a second. That's sort of like the Cliff Notes version of this design guidance. I do want to mention that it's not the only design guidance that's out there. So there's also design guidance that's published by the American Society of Civil Engineers. There's an international building code, lots of these different design documents. And even though there are all these different agencies that are contributing to these design documents, something that's important to keep in mind is that the language is very similar. They try to write in such a way that you know exactly what you need to calculate and what that means for the safety of the structure. So if you can navigate through one design code, deciphering these other codes is relatively similar. Again, if you have any questions about that PowerPoint, it's just a lot of background information. So hopefully that was sort of a decent introduction to what we'll be talking about today. And for the next few days, as we go through the API design criteria, I'm going to exit this PowerPoint and let's jump back to the notes. So I'll stop sharing and go back to the notes. And so here's where we'll sort of see how this goes. I'm going to try to just take the notes as usual, and then we can, kind of see how we can adjust. Let's touch base in office hours as we go. So this is a new unit. So we're starting with letter I, and I'll title this Offshore Structural Design. And API design criteria. And we're still recording. Cool. Okay, great. So just as a brief intro, we have that PowerPoint. So please have a look at that for types of offshore structures and designs. The big takeaway from that PowerPoint, so the takeaway is that we know how to find internal forces and deflections So again, that's going back to this direct stiffness analysis to find the reaction forces and deformations, deflections, and rotations in these different trusses and frames or beams for any given scenario. We could alternatively, instead of doing the matrix analysis, we could plug these structures into STAD and run that analysis as well. And that'll give us these answers. But now we want to know at what load or deformation will the structure fail. So sort of saying how much is too much, or when will we expect that our structure is not sufficient to withstand the loads that it is being subjected to. And design standards are our way of setting, one, what load we should design for, and two, making sure that we can protect our structure from that design. So design standards set the maximum allowable load for a structure and dimensions so that the structure is safe. Cool. And again, as I mentioned briefly in the PowerPoint, we'll be focusing on the API recommended practice. And specifically, we'll be focusing on the sections related to column or pile design. The full code, I would definitely recommend taking a look at it. It's very cool kind of to see how they consider all of these different things. They really consider everything from the materials you should use, the corrosion guidance, to the acceptable loads. I have posted in our lesson 25 folder sort of a bit of a cliff notes. It's 4 pages long, and it kind of talks about the main criteria that we care about when it comes to pile design. So there's 5 main criteria to check. We'll put these in the notes. And then I think the best way to do this is to sort of learn by doing an example very slowly. So for the notes though, let's satisfy 5 design criteria. And those 5 criteria that we have to satisfy are axial compression, to prevent local and global buckling, bending. So this would be due to like a transverse loaded moment. So if this is my pile, we've got vertical loads coming here. Transverse loads would be something coming this way, maybe like a wave or a wind current. And then shear. We also have hoop stress, which is due to hydrostatic pressure. And finally, we have to consider combined axial plus bending stress. And let's go ahead and set up an example and then just slowly work our way through the calculations that we need to satisfy each of these criteria. Again, we're going to be following these cliff notes very closely. So if you want to have them sort of on like the side of your screen, I'll try to pull them out when I have things to talk about and to write the really key points here in the notes. So let's do an example. I'm going to shift down just a little bit and we can go to our example, which is to check that the following column satisfies API design criteria. And our column, we have, it is coming up to the surface of the page. We have a 50 kip load acting at the top of the column. So here's our water table. Here's the depth. The total length of the column and water depth is 100 feet. And we have, so here's our column, a 120 pound per foot load acting along the shallowest 50 feet. So this is 120 pound per foot, or pound per linear foot. And then as you move towards the bottom of the column, maybe you don't see as much load in this direction. So it's 50 pounds per foot. Again, the vertical extent of these loads is 50 feet and 50 feet. And we're also given the column dimensions. Oh, and I'm sorry, I forgot one load too. We have a 250 kip foot load applied at the top of the column. Maybe that's due to the platform and where instruments are located or where the wind is blowing. So this is, again, 250 kip foot in the counterclockwise direction. Our column dimensions, it's a hollow column or a pipe. And so we have an outer diameter, which is going to equal either D outer, so D sub 0, or sometimes the API design criteria will call this D. And this is equal to 48 inches. The thickness of the column is equal to 1 inch. And we know that the yield strength is 50 KSI. That's yield strength. And the elastic modulus is equal to 29,000 KSI. So we're building a steel column in 100 feet of water depth. I like to think about this. This is sort of one of my favorite times of year. This year we're in a bit of a drought of bracketology. But I do like to think about this as sort of following a bracketology style or a tournament style roadmap, where our column is sort of has 5 play-in games to see if it's safe. So our roadmap, we can think of it as sort of a bracket where we have first our column is going to go up against the axial compression test. So is it safe for axial compression? The winner of that, hopefully it's the column, but if not, then we stop. But if it wins, then we move on to the bending check. Again, if it can get past bending, we'll go against the shear. If it goes past shear, we'll check it against hoop stress, or again, that's due to hydrostatic pressure. And then finally, we'll check it against combined axial plus bending stresses. And after that, we'll see if the design is safe. So this is sort of our safe. And if it's safe, then it's the champion of this API bracket. So that's kind of where we're going from here. Again, today we're just going to do the axial compression check. Although before we can even start with these checks, the very first step, or step 1, this might be step 0 depending on who's asking, but the first thing we need to do, so step 1, is to find the maximum loads that this column experiences. So find our maximum shear, Vmax, our maximum moment, Mmax, and our maximum compressive load, Pmax. So these are the max shear, moment, and axial loads that the column experiences. You can find these loads using statics. So since we have a cantilever style beam with basically this column is fixed into the seafloor, we know that the maximum values are going to occur at this fixed end where you have the reaction supports. So if I sum the forces in the x direction, I'm just going to give the answers if that's okay for the sake of time, but you can go ahead and sum the forces in the x direction. So this is E, sum of force in the x direction. That will tell you your maximum shear is equal to 18.5 kips. If I sum the forces in the y direction, equals 0 equals P max, which is my reaction, minus 50 kips. I needed to put units up here. That's our only force in the y direction, so this gives us P max is equal to 50 kips. And again, if I sum my moments about this fixed end, I can solve for M max, which will be equal to 1,762.5 kip feet. So these are the values that I'll be working with when I want to find the actual shear, axial, and bending stresses, which is what I'm comparing. So I'll find the allowable ones, and then I'll compare these stresses to see if the structure is safe. All right, so once I have these loads, I'll shift this up a little bit, and then we'll sort of. All right, so once I have these loads, I can move on to step 2. Which is my axial compression check. And essentially what we're doing here is we're checking for column buckling. And let's go ahead and take a step back and actually define what is column buckling. So to do that, let's define a column as any member loaded axially in compression. So axially means that it'll be along the axis of the column, and compression means we're sort of pushing down on this column. Buckling is the lateral deflection due to compression that moves the load away from the column's axis. So for example, if you had something like a Twizzler and you push down on the Twizzler, that Twizzler will buckle because it'll sort of push the load away from the axis and it'll kind of fold in half. This is a big problem for structures because it can occur below the yield stress, below Fy, and typically it occurs without warning. So you're not going to see a lot of cracks that are sort of saying, hey, something might be wrong here. So it's very catastrophic and sudden when this type of failure happens. For an ideal column, we have buckling at the Euler buckling stress, so P sub E, which is equal to pi EI over L squared. That's Euler's equation. Where P is equal to your axial load at buckling. E is your elastic modulus. I is your moment of inertia. And L is the total length of your column. Now, a question that I have for you guys is, should we use Euler's equation for design? Yes and no. So it's good to base design on theory. So it's good to use this as a basis for how we can design our column. But we have to account for real world non-idealizations that exist. So real world uncertainty. So need to account for real world uncertainty, which includes things like the column N conditions, are they both fixed? Is only one fixed? Do you have one that's pinned in some way? Is there any load eccentricity? So is the load applied perfectly on the column's axis, or is it skewed a little bit? Are there any residual stresses? Etc. And so therefore API doesn't use Euler's equation. They set critical buckling load and then an allowable stress, which is what they use to ensure whether the actual stress is too much. So API sets a critical buckling load, PCR, and allowable stress, capital F sub A, to ensure that actual stress, or lowercase f sub A, is safe. So that's some background. Let's go ahead and talk method. To do that, we're going to follow along with this a design criteria. So I like to break it up a little bit into kind of subsections. So the first thing we need to do, the big, I guess, chunk that we're going for with this next set of steps, is to find our critical buckling stress, PCR, and allowable stress, capital F sub A. The first thing we need to do, so this would be 2.1.1, is to find our effective length. So effective length which depends on the N conditions, or how is our structure attached at both the top and the bottom. So for this, we have an equation. We can say that the effective length, L sub E, is equal to K times L, where L sub E is our effective length. L is our actual length. And if you go back and look at your notes, your actual length for this problem is equal to 100 feet. That's the length of our column. And then K is a factor based on the end conditions. And so for that, we'll see either table C-C 2.2 or table 61.1 from our Cliff Notes. This table is what's given in API, or they reference this table from AISC. Basically, it tells you, depending on your column, what should I use for my value of K. So a built-in, this is the same thing as a fixed end. So you can have something like a built-in, and if it's fixed on both top and bottom, you can actually reduce your effective length, so it'll be a value less than 1. You have all these other conditions. If you have fixed free, which is what we have, so built-in dash free, we're going to use a K value of 2.1. So we're increasing our length by a factor of 2 to sort of add that factor of safety for design. Totally fine if you want to use this table. It gives you a little bit of an annotation of what these different symbols mean. Ours is built-in free. Again, though, make sure you use the recommended value, not the theoretical value. This recommended value is a little bit more conservative in general. So again, just as a note, use recommended value. And since we have fixed and free ends at our column, that means that our value of K is equal to 2.1. Great, so our effective length then is equal to 2.1 times 100 feet, or 210 feet. Next, we can follow along. So we've already finished page 1 of our Cliff Notes. So the next thing to do is to check the slenderness ratio of our column. Sorry, I'm off the page. But we're going to check the slenderness ratio. So step 2.1.2 is to check the slenderness ratio, SR. And for that, our equation is SR is equal to our effective length over the radius of gyration, which the radius of gyration is equal to the square root of our moment of inertia divided by the area. So again, just to get these in the notes, R sub G is our radius of gyration, which is equal to the square root of I over A. Just as a note, the API design guidance calls this R. But I think that R is easy to confuse with radius. And I is our moment of inertia. For a hollow pipe where we have an outer diameter and an inner diameter, we can calculate the moment of inertia. So I pipe is equal to pi over 64 times the outer diameter to the 4th minus the inner diameter to the 4th. So for us, this is pi over 64 times the outer diameter is 48 inches to the 4th minus the inner diameter is 48 minus 2 times our thickness, so 46 inches to the 4th, which is equal to 40,789.7 inches to the 4th. And then area is A, so the area of a pipe is equal to pi over 4 times the outer diameter squared minus the inner diameter squared. Sorry, this should be an I, which is equal to pi over 4 times 48 inches squared minus 46 inches squared, which is equal to 147.7 inches squared. Plugging all of these numbers in, we can calculate our slenderness ratio, which is equal to 210 feet, divided by the square root of 40,789.7 inches to the fourth, divided by 147.7 inches squared. Okay? Not okay. We have to be careful about units in really every step of the API design guidance. So something that's really important is to make sure that we're dimensionally consistent on top and bottom. We have feet here. This will be the square root of inches squared, or inches. So let's just multiply this times 12 inches per foot. Now we have inches on top and bottom. So we get that our slenderness ratio is equal to 151.6, and it's unitless. All right, the next thing that we need to do is to check for local buckling. So I'll slide this up. So this will be step 2.1.3, is to check local buckling, which is a problem if D over T, so if our diameter over our thickness is greater than 60, we may have inelastic local buckling. And if you have that, I'll just show this in the clip notes. If you have D over T greater than 60, this is on page 2 of your clip notes, then you have buckling that could occur at the minimum of F sub XE, which is our elastic local buckling stress, F sub XC, which is our inelastic local buckling stress, which is an issue when D over T is greater than 60, or our yield strength. We have D over T is equal to 48 inches divided by 1 inch, which is equal to 48, which is less than 60. So we have no local buckling, at least inelastic. So therefore, we can have buckling at the minimum of these three equations. So similar, this elastic local buckling, but we're now going to set this inelastic local buckling equal to our yield strength. So we really only have two things to compare. So we have F sub XE, which is equal to 2 times a coefficient times E times T over D. F sub XC is equal to Fy. And then finally our yield strength, which is equal to 50 KSI. So we can fill in these two already. Defining some terms, we've already mentioned this, but we have FXE is our elastic local buckling stress. F sub XC is our inelastic local buckling stress. And F sub Y is our yield strength. And then we have C, this C value here, is equal to our critical elastic buckling coefficient, which is equal to 0.3. Similarly, E is the elastic modulus, T is the thickness, and D is the diameter, just like before. So when I plug in these values, I get 2 times 0.3 times 29,000 KSI times 1 inch over 48 inches which is equal to 362.5 KSI. The minimum of all these is going to be 50 KSI. So for our beam, we're going to move forward with min equals to 50. So for our beam, we have min equals 50 KSI. All right, guys, we're almost done with this section. I think we have probably about 5 more minutes. If I spill a little bit over on this lesson, I'll try to cut down the next lesson to make sure that we're averaging about 50 minutes. But let's go ahead and finish the axial compression check. So the next step, we have 2.1.4 is to find the column type based on our slenderness ratio C sub C. C sub C is defined as the square root of 2 pi squared times the elastic modulus divided by this minimum value we found in step 2.1.3. Plugging in values, we have 2 pi squared times 29,000 KSI divided by 50 KSI. And so we get C sub C is equal to 107. Next, we're going to compare C sub C to our slenderness ratio that we calculated earlier. And so we have our slenderness ratio is equal to 151.6, which is greater than C sub C. So if we look in our cliff notes, we see we have kind of 2 tracks to follow. If we have our slenderness ratio is greater than C sub C, we have an Euler column, which is long and slender. That's what we have. And we have these 2 equations for our critical buckling stress and our allowable stress. If the slenderness ratio is less than C sub C, we either have an intermediate column, which is for a slenderness ratio greater than 10, or a short column, which is for a slenderness ratio less than 10. And that's when you have your equations change slightly when you're calculating PCR and capital F sub A. So just keep that in mind. We have an Euler column. So this means that we have, so therefore, our critical buckling stress is equal to pi squared E over SR, our slenderness ratio squared. So that's pi squared times 29,000 KSI divided by 151.6 squared, or PCR is equal to 12.5 KSI. And our allowable stress, capital F sub A, is equal to 12 over 23 times our critical buckling stress. So we get F sub A is equal to 6.5 KSI. This is what we'll compare to our actual stress to determine if the structure is safe. So step 2.2 is to find our actual stress. Little f sub A, which is equal to our maximum actual compressive load, P max, divided by our area. So plugging in numbers, we can say that this is equal to 50 kips divided by 147.7 inches squared, or lowercase f sub A, our actual stress, is equal to 0.34 KSI. And the very last step we have for this check is to compare our actual stress to our allowable stress. So compare our actual little f sub a versus our allowable capital F sub a. If f sub a is less than capital F sub a, we have a safe structure, and so we can continue. If not, we need to redesign. And this is kind of the final step for every single check. In our case, we have 0.34 KSI, which is our little F sub a, or our actual stress, which is indeed less than 6.5 KSI, our allowable stress. And so our structure is okay. And so we can move on to our bending check. We'll pick up with bending next time. Thanks so much, guys, for hanging in there with me. I know this was a ton of info to cover today. I'll sign off and say goodbye. Thank you guys again so much. I hope you guys are having a great time. And again, stay safe and looking forward to seeing you soon.